Okay, so today, after a little break in our interaction, so let us resume our discussion on baseline correction. And in last lecture, we discussed about the errors and kind of corrections that are required for analog accelerograph, which were the first strong motion time history recorders that came along, and they did give us a lot of information and led to significant development in earthquake understanding earthquake ground motion and evolving design provisions to withstand earthquakes. Next in technological development, logical transition was analog instruments were replaced by digital instruments, and the major problem with analog instruments that did not have uh, initial part of the record. Most sometimes it was also possible, particularly in near field region, that the instrument triggered only after the S waves had arrived at the station. Only S wave were strong enough to trigger the instrument. So the entire P wave portion was lost out, and obviously initial conditions were not available, and without those initial conditions, any integration is not possible, and it was only a guessing game. What would be the ground velocity and ground displacement uh, when it is derived from the ground acceleration? And this is very critical because the seismological instruments typically go out of scale in near field region. They are so sensitive, the seismometers, uh, that in near field region, when the motion is so severe, none of the seismometers can actually capture that record. So only the uh, strong motion instruments, accelographs, can actually record the motion. And although the acceleration is fairly reliable, but velocity and displacement, which is of primary importance, primary use for seismological interpretation, those are very unreliable quantities derived from uh, accelerographs. So digital accelerographs, they in a way circumvented or alleviated this problem to some extent, in the sense that it was possible to have uh, some kind of buffer memory, and which could be padded, which could be added to the main event after the instrument triggered. So it was possible to have a programmable setting for pre-event time. That means the total length of the record which will be preserved before the instrument was triggered, and then post-event time as well, after the instrument uh, base acceleration fell below the threshold. Then how long the motion instrument should keep on recording the motion, and that would be appended to the triggered section of the record. So in the hope that the total earthquake is somewhere in between this recording that we have. Of, of course, for NHPC that is not a problem, because your instruments are uh, uh, always on recording mode. So there is no chance that you would miss the event. As I understand from the standard operating procedure of NHPC strong motion program. But that still leaves the problem of, I mean, you have a continuous stress, and suddenly you have strong motion looking in. But where exactly in that continuous trace? I mean, continuous trace is also not a dead line. Your continuous trace is also going to be, I mean, it will look like something like this, and suddenly it would start bringing up and something like this. So where in this portion, obviously it is obvious that somewhere here the earthquake, this looks very different from the background record that you have. But where in this background information, where does the where is the beginning of earthquake? Rest of this is all background noise. The recording instrument also has a native noise measuring system, recording system, and it will always have some kind of fluctuation, although it might be very small compared to the total range, but it will never be a dead, any instrument recording, much I would like to have it, but it will never be a deadline like this, right? So it will always, you will always have, any recording instrument will always have this kind of uh, oscillations. So that complicates the matter, and we need to look at where is the find out where is the beginning of the earthquake event, and the tool that we use. All of you must be aware of this. This technique is very commonly used in seismological instrumentation. I am told that this is very common for something called phase picking. I hope you are aware of this phase picking, where you
Yes, sir.
so you do this by performing considering this STA by LTA average, right? So that's
Mm-hmm.
actually short term average.
Long term and short term average. We take the ratio of that.
Short term average divided by long term average, and the way we do that is you have this window. So once part, let's say this is what we call as a leading portion, very short duration is a short window, and followed by a long window. So there is a finite number of data. So let's say, for example, if we consider 50 samples for short-term window and short-term averaging, and let's say 200 samples for long-term averaging. So that typical setting of digital accelerographs is to have 200 samples. Samples per second. So when we say 200 samples of long window, so that is 1 second record, and if I say maybe 50 second or even 20 second, 20 samples, so that would be about, if I say 20 samples, let's say 20 samples should be good enough. And this is 200 samples, right? So 20 samples, that means we are looking at 0.01 second resolution. So what we do here is take out the average STA at time Ti. So that these are the samples. Let's say this is the time Ti. So sigma j is equal to I minus 20 to I absolute value of A Tj. We can square it, or either we can add the absolute values or we can square them and add them, whatever. And LTA would begin just after that. It would start from j is equal to I minus 220 and stop at I minus 20. So at this point, so we start computing from accumulating sum from the first point, come up to here, and that would take the average of that. So this would be divided by 20 and this would be divided by 200. Right, so these are the sample data. So once we do this, then STA by LTA ratio, the moment it increases beyond 1, if there is no record, then obviously STA by LTA ratio will be close to 1, and the moment it senses that some motion is there which is other than the background noise, some seismic activity, so this term, this increment, this summation would increase first before it begins to have any effect on long-term average, and thereby increasing the STA by LTA ratio greater than 1. And wherever we obtain this STA LTA ratio greater than 1, that we take as the beginning of the earthquake event. And that's how we will do this exercise. That's as I said, from today we will start playing with numbers, and you can take this as the first assignment for take one of your records from your database and do this STA LTA by STA analysis and try to figure out where the earthquake event has actually started, what is the beginning of the earthquake event. Now, technically, at what happens at the start of event? At the start of the event, obviously the ground is at rest. Ideally, the ground should be at rest. So the displacement should be 0, velocity should be 0, acceleration should be 0. So all three components, all three motions have to be 0. Initial conditions have to be 0. But the problem is, this is fine if we were we still do not appreciate, most of us do not appreciate the nuances of digital signal processing or discrete time signal processing, discretely sampled data. So there is we very conveniently assume the discretely sampled data interconnected by straight lines, and in plotting it gives you, it appears to us as a continuous data, but that is far from the truth. What we actually have is a discretely sampled data, and even that discretely sampled data is not uniform. The values are not uniform. Every instrument, every measuring instrument has a least count, and so does our accelerograph. And that's where the digitizer resolution comes into picture. Most of the accelerographs that we have, they have 16-bit resolution. Modern times we are beginning to get 18-bit resolution accelerographs. But whatever may be the resolution, there is a finite quantization. There is a least count below which it cannot, the sensor cannot, or the recorder, I mean your measurement system cannot have any record below that. So the offside of this is, no matter what, I cannot have, I can only have discrete values. I mean, it can start from 0, next value I can only have at this, next value I can have only at this, next value I can only have this, and so on. So if the actual value is somewhere in between, there is no way I can get this information. It will be either reported as a lower bound or upper bound, depending on the whatever round of strategy that has been encoded. Right, so this complete bit level, whatever total number of bits, so 16 bits or 18 bits, so that will the total range that will be divided into those many configurations, and there will be certain quantization that will be the least count, and we cannot, our accuracy is only half of this. That's the resolution. We cannot resolve any smaller than half of this quantization level. So if the value sensed is more than this half of this value, it will be reported as a higher value. If the value is less than this half of this value, it will be reported as lower value, and so on. So even that is an approximation, and it adds to the error. Even in the acceleration, we are sensing the acceleration, we are recording acceleration, and even in acceleration that may there is a quantization error. So does it make any difference? And then so there is something called quantization error, and then there is something called the sensor. It keeps on drifting away. It's null. You might have observed this in various sensors that you deploy. Over a period of time, its null position changes, its null position shifts, and you need to keep on periodically, you need to keep on adjusting the null position. So that is referred to as DC offset. So that DC offset also, I mean, you can never be sure that what you are getting is there is no DC offset in the recording. So you need to, and that DC offset is unavoidable. That comes from the instrument, I mean the components fatigue in the instrument, or misalignment, or whatever that may happen, mechanical fault, mechanical misalignment of the components in the sensor, and so on. So there can be DC offset, so that's a constant shift. So this baseline, it will, I mean, although if the null position is like this, the sensor will shift somewhat constant level down, and it will oscillate around that DC offset. So this is what we refer to as the DC offset. Now, all these quantization level also adds to this DC offset because we cannot go exactly to 0. There might be some error because of that. So effectively, its manifestation is similar to DC offset, but uh, DC offset can be a little large. Quantization error, effect of quantization error, magnitude wise, is limited by the this half of the least count of the measuring system. So what is the effect of this? So if I have some quantization level, I mean some constant level, so A hat T is equal to what I am recording. So this is what I have recorded. This is the correct motion. Plus some constant drift. Right? So if I find the try to derive the velocity from this, so that gives me integral of at dt and plus delta times dt, and this is of course from 0 to t, and this is obviously Vt minus V0 if we find. So that is the difference between the final velocity and initial velocity plus delta t. And now if I try to figure out what is the displacement coming from this, it would be 0 to t so again it would be there would be some terms related to this, and the error is here. So this will again be, there would be some terms related to this plus delta t square by 2. And that is why if you look at it, the acceleration might look like this, the velocity trace, if you look at it in many of the records, you might find a linear trend somewhere here, and the displacement would actually be looking something like this. So this is the parabolic trend that you see. This parabolic trend is coming because of this DC offset error. And if you remove this, then the displacement would become more reasonable. Now, why this is a problem? Because this is monotonically increasing. See, this is t square. It increases exponentially, and the estimate of displacement, particularly for seismological and even for earthquake resistant design of lifeline facilities like pipings and tunnels, etc., bridges, etc., the ground displacement is a very major criteria. What is the maximum ground displacement that we are looking at? If I have to design a bridge which will cut across a fault, then I need to account for the what is the displacement that might happen along that. So this displacement estimation can be way off the mark. Actual displacements might be very small, but if I derive these displacements from this accelerogram, digital accelerogram, then the velocity would be also, if I'm not careful, then velocity will have this linear trend. It will keep on increasing, and then the displacement will have this quadratic term riding on top of the which will govern the actual displacement is somewhere here because of these velocity traces, actual ground acceleration and velocity traces, and that would be figured added by, that would be offset by this quadratic variation, and this may completely cloud the uh, interpretation of the displacement, ground displacement, and therefore it needs to be resolved. And there are 3 steps that are normally used. There are various ways of different schools of thought for digital baseline correction or baseline adjustment of digital accelerogram. We will we will cover one of the simplest one, which is covered, which is discussed in the article that I shared with you. And once we build some confidence in dealing with this, then it becomes easier to understand and relate to other processing schemes. Most of the other processing schemes are actually modification of the schemes which were derived for analog instruments, uh, primarily Trifunak and Lee from University of Southern California. They started developing it in early 70s, and at that time they were only looking at analog instruments, and subsequently with they kept on modifying this for applying it to digital accelerograph data. But as you can see that it's quite a few of baseline correction involves some kind of educated guesswork. So there is nothing which is the correct procedure. We work with whatever is available with us and try to make sense of within the available resources. So in that respect, this particular scheme that is proposed by Taiwanese group is a very simple scheme and very easy to implement. And let us start with that, and then we can pick up on the later portion. But conventionally, we have there are 3 stages. Strong motion data processing. Again, it is more of a legacy matter coming from analog instruments. So volume 1 data, these are called raw accelegrams. Right, so these are digitized values sampled from photographic films. Right, so there is no correction applied here. It's just the digital, I mean the record has been converted from analog to digital values, because for processing on digital computer you need the numbers, you cannot process the film. So those films obviously then they need to be enlarged, optically enlarged, and then manually uh, or semi automatic large digitizers were pushed into service, and to convert those analog traces into the digitized discretely sampled values, and that form the volume 1 data, that is raw accelerogram. From this, volume 2 data, this is derived by instrument and baseline corrected accelerogram and derived velocity and displacement time histories. So once we have this volume 1 data, then knowing the instrument characteristics, what are the sensor characteristics and its natural frequency, damping, etc., we can implement the instrument correction if required. That depends on the frequency range we are operating on, and sometimes it may be required, as I discussed earlier, if we are operating in the range where the sensor amplification is very significant, then instrument correction is required. And after applying the instrument correction, then baseline correction is implemented. Baseline correction or baseline adjustment. Baseline adjustment is the more recent usage to indicate, to explicitly indicate that we are not very sure about whatever we are doing, but we just hope that it is the right thing to do. So after instrument correction, if required, we apply the baseline adjustment to the accelerogram, and when we do that in the process, we also derive the velocity and corresponding displacement time histories for use. And once we have this, then other set of derived data is required. So volume 3 data, after this accelerogram processing, then we go to computation of response spectra, Fourier spectra, and intensity measures, or also known as damage potential indicators. So this is volume 3 data, that this is derived after we have this baseline corrected instrument and baseline corrected accelerogram. Then using that accelerogram, we compute the response spectra. We already discussed the concept of response spectra. So all three components of ground motion, we compute the response spectra for a set of natural period for a set of damping ratio, and similarly Fourier spectra for all three components. And then for all three components we also compute the intensity measures or damage potential indicators, such as Arias intensity or Araya damage potential, and effective peak ground acceleration, effective peak velocity, and similar such measures. There are several of those. So all of those are tabulated and recorded and made available for public consumption. So any strong motion instrumentation program, the standard data processing should involve all these three steps. So at the moment, what we are doing at NHPC is we are stopping at volume 1 data partially. Even that volume 1 data is not completely available because we have not really identified the beginning of the event correctly and the ending of the event. So that has to be looked at, and once we do this volume 1 data, isolate the earthquake event, then we can take up and go ahead with the instrument and baseline correction, corrected accelerogram, and derive the velocity and displacement time history. So how do we do that? I mean, integration, I mean, velocity and displacement is a process of integration. We just integrate the data, and there are different ways of doing it. Either we do it in time domain or we can also do it in frequency domain. Frequency domain integration is very simple by just dividing by I omega, and then again for taking the inverse Fourier transform, we effectively compute complete the integration process. So that is typically done in most of the time now. The integration is done in frequency domain by division of I omega, and then in computing the Fourier spectrum. So if A omega Fourier transform of acceleration, velocity, and displacements. So let's say A omega is the Fourier transform pair of AT, then V omega is the Fourier transform pair of velocity, and D omega is the Fourier transform pair of dt. Right? So now Vt is derived as integral of At, and dt is derived as integral of velocity. So now integral is done very easily. If I say At is A omega e to the power I omega t going from minus infinity to plus infinity d omega, then integration with respect to dt is going to be interchanging the integration. So a omega goes out, e to the power I omega t dt d omega, and that brings us I omega a omega divided by I omega e to the power I omega t d omega. So that brings us this v omega. I mean, if it is a Fourier transform pair, then that means v omega is equal to so that makes it very simple. So for in frequency domain, this is a very easy way to implement. So v omega is particularly frequency by frequency 1 over I omega times a omega, and d omega is just minus 1 over omega square a omega. And once we have this Fourier spectra of velocity and displacement, we just take the inverse Fourier transform and we get the velocity and displacements. And all these Fourier transform, they may appear complicated, but all these are native functions in Octave or MATLAB, and just it's a matter of calling appropriate function, and we can do this analysis. Now the only problem here is it goes from minus infinity to plus infinity, so there is somewhere 0 here. What happens to 0? This will blow up omega, this will blow up, this entire thing is going to blow up at omega is equal to 0. So in order to eliminate that, what we do is most of this is our recording, this alignment or whatever is the systematic error, those are eliminated by those are very low frequency errors, and those are eliminated by low frequency errors are eliminated by using a high pass filter. By using a high pass filter on the accelerogram data, and once we do that, then obviously this becomes integral becomes from some small value to some large value. Obviously we do not have we do not need to go up to infinity. It will terminate at the Nyquist frequency. So we will go from some small value, some small frequency up to Nyquist frequency, both in positive and negative range, and that will eliminate this issue of omega is equal to 0 blowing up. So we get the velocity Fourier amplitude, we get the displacement Fourier amplitude, and then we just implement the invoke the inverse Fourier transform to get the displacements and velocities. So how do we so this is the process that we do for calculating the velocity and displacement from acceleration, but before that acceleration has to be acceleration trace has to be corrected. and that is done. I mean, all these errors that I mentioned here, uh, quantization error, DC offset error, systematic error because of misalignment and so on, all these are eliminated by two steps. Detrend the acceleration trace. And second is use high pass filter on the acceleration data after detrend. So once we do this, then we can go ahead with the further processing. There is another issue that will happen after further processing is uh, which is not visible in the acceleration trace, but which will be there because of again quantization error, that velocity may not be actually implemented as may not be captured as a zero value, because some initial velocity, if there is some initial velocity because of the quantization error, that because of the we are sensing the acceleration, so constant velocity will appear as a zero acceleration in the acceleration trace. So that constant acceleration initial velocity portion, that may again lead to a linear trend in the displacement because of the integration. So that constant velocity, initial velocity correction has to be applied after we compute the velocity motion, and then that velocity has to be used for computing the displacements. So I'll stop here. Any questions? And then you can read the article that I shared, and in the meantime tomorrow I will share a set of problems that you can work on, and using the uh, some of the data, some of the time histories from NHPC database, and we can discuss the results in our next interaction. So by tomorrow I shall be able to send the uh, set of exercise problems. So any questions?
Sir, I have one just now you said STA by LTA ratio, which we can start for identifying the earthquake event.
Yeah,
So, I would like to start applying this for our some of we can try it with some of our data.
sure. You
Like I
can
was just thinking,
you can start
sir,
right away. That was one of the exercises that I was going to include. So you can start right away. You don't have to wait
so
for
we can pick up, sir, any time, any data, or it has to be like we can pick up any data
yeah,
of
any
any
data,
magnitude, any.
any data from your database,
Okay.
that should do.
Okay. So on trial basis, we can try some and then we can share it with you and discuss, and then we can apply it to the entire data set then.
Sure.
Yes, sir.
Yeah.
So for that, do we need how do we proceed with that? Do we need to prepare some algorithm or something? How?
Yes, a little bit of logic needs to be built in, because that window has to keep on shifting. That time window, that
Yes, sir.
long time average and short term average, that time window will have to keep on shifting. So that's a very simple already wrote some a rough sketch of that algorithm. If you look at it, so
Okay.
this is what the algorithm is. It will be something like this. So
Okay,
it will
sir.
keep on shifting. This index keep on shifting. So these indices
Hmm.
of this summation will keep on shifting. That's
Okay.
all.
So, sir, we will give it a shot, and then we can discuss it with you.
Yeah, sure, sure.
Yes,
Please
sir.
do. Yeah. Okay, so I'll stop recording here and I'll
Yes,
upload
sir.
this lecture today.
Thank you, sir.
Thank you. Thank you, everyone. And Happy New Year to all of you once again.
Yes, sir. So, same to you, and hope, sir, you have recovered well from your eye infection, sir.
Yes, yes. So far, so good.
Okay, sir.